I forgotten to send you the note. I thought I sent you yesterday, but didn't realize that we are now on page 83, oscillations, topic 17. We are going to look at simple harmonic motion, its ideal case. And then after that, energy in simple harmonic motion, damp and forced oscillation. For simple harmonic motion, we will define the term. Right? There's a definition for simple harmonic motion. In terms of acceleration, then we define the term amplitude, period, frequency, angular frequency, oscillations. And we look at how displacement, velocity, acceleration varies with time, and how the velocity, acceleration varies with displacement. Then 17.2, we look at energy in simple harmonic motion, right? Kinetic, potential, total energy changes with time and displacement. And under damp and forced oscillations, we will look at resonance. Okay, so today we will start with looking at review some of the maths about sinusoidal waveform, sine curve and cosine curve. Okay, let us make a start. You can use your textbook. There's a general equation of a sine curve, right? Sinusoidal curve, sine curve. D is for vertical shift, right? Shift it upwards or downwards. Positive means upwards. This is the dependent variable. X is the independent variable. Usually we use time rather than X. Or sometimes we will use that theta angle. Theta stand for Bx. A is the amplitude. How large is the oscillations? And then the B, the coefficient, is to determine the period. C, phase, tell us where the oscillation starts. Right? But we won't be going too complicated. Okay, the main thing is you need to know sine curve. Right? There's a sine curve. You need to know radian. Okay, y equals to a sine theta, sine x, amplitude a. So in this case, amplitude is 1. No? If you don't want 1, you can put a there. No? Right? There's the a there. And this is minus a. Right? Pi radian, half, half, half radian is, half pi radian is 90 degrees. Pi radian is 80 degrees, 180 degrees. 3 pi over 2 radian is 270 degrees. And 2 pi radian is 360 degrees. Okay. Properties of radian. Right? Half pi is 90 degrees. Pi is 180 degrees. 2 pi is 360 degrees. Note, sine 90 degrees or half pi radian is 1. 80 degrees is the amplitude of 1. Sine pi or 360 degrees, 2 pi is 0. 270 degrees is minus 1 or minus a if you are using this equation. This is a cos graph. Cos 0 is 1. Cos 0 is 1. Cos 90 or half pi radian is 0. Pi is minus 1. Okay, so you A in this case is 1, that's the amplitude. Changing amplitude, in this case, right, we're changing this amplitude there. Instead of 1, in this case, is amplitude is 2. In this case, amplitude is 5. 5 there. The waveform is still the same. Haven't changed that. Still pi is 0. Pi is 0. Right? So if this is a sine curve, negative amplitude minus 1, then it just invert it. Invert it. Okay, if we add 1 to the sine curve, right? If we add 1 to sine curve, we just shift it outwards by 1. No? 1, this point shift by 1, maximum shift by 1, minimum shift by 1, right? 0 shift by 1. Okay, shifting vertically D lah. D in this case is 1. Okay, if we add 1 to here, 1 to here, then we are just basically shifting it to the left, no? Negative 1, right? To the left. A positive phase shift of C actually indicates a shift to the left. That's your C. Shift it to the left, minus 1. In physics, we normally will use Y, and then A is the amplitude. Instead of X or theta, we use omega T lah. And omega is 2 pi over T lah. Any comments so far? Anything not clear?
I don't know.
The curve shifted pi, half pi radian to the right. In this case, you shift it to the right, half pi radian. So that is your equation. And then it becomes this this one shift it to here. This point 0 shift it to here. That's what is happening here. And this becomes a minus cos graph. Changing coefficient, right? Pi is 3.14. Right? Changing this coefficient B. Right? This one cycle, 2 pi is pi. So if it's 2x, still the same scale. Right? As well as stretch it bigger so you can see, but still the same scale, 2 pi, 2 pi, but there are 2 cycles now. 2 cycles. This one cycle, this another cycle. Stop me if you need to ask.
Okay.
Right? This one just basically a sine curve. Change the amplitude. Instead of 1, we change it to 2. And also 2 cycle. Right? We change this one to. So instead of 1 cycle, 2 pi there, pi there. 1 cycle is pi. Right? There's 2 cycle. Right? Sometimes we use pi radian, sometimes we use time. Usually we use time for this axis. Okay. You have to know that this is your sine curve, right? If you square it, negative becomes positive. It's still a sine curve, right? You can show it using your maths, right? Sine 2x equals to that equals to cos square x minus sine square x equals to 1 minus 2 sine square x. Then subject, subject this one, take over there, you get this equation. So it's still a sinusoidal graph. Sine square x is still a sinusoidal graph, but it's of this different form. This for your benefit only. You don't need to know the math involved, but just to convince you that it's a sinusoidal. But you need to know
Sure.
how to draw lah. Yep.
How many chapters are there in A2? Is this the last chapter?
A2 is I think 14 topics.
14?
1 4.
Oh, so uh,
We are covering the
what,
sixth topic.
what's the last chapter?
Last sector is cosmology, I think. Astronomy.
Chapter what? What number?
That one I have to check for you. Can't remember.
Oh, okay.
Right? This is your sine x curve. This is your sine square x. Right? By squaring it, you change it to 2 cycles. This is 1 cycle. A minimum to minimum 1 cycle. That's another cycle. While you sine x is 1 cycle. Right? Don't draw it this way. This is wrong. For alternating current, where you square it, if it's a sine curve, it's not this way. If there's your sine, you square it. That one correct, but this part is wrong. Same thing. Negative, you square, become positive. Write down the equation for the following graph. What is the equation for this graph? Yep.
The sine
Give me the equation.
minus sine.
What is the equation?
Negative sine.
Y equals to what?
Y equals to minus sine. Wait, minus.
Right? Minus
Oh,
2
yeah,
x,
minus
x.
2. Yeah, yeah.
Okay.
Okay. Yeah.
Okay. That's your summary of your sine graph. This is your sine graph, the red one. This is your cosine graph. What is the equation of the sine graph? The green one. What is the equation?
Y equals to 4
Yep.
for sine. Uh,
Amplitude is 2. Right?
eh,
Amplitude is 2.
pardon. Oh, yeah, yeah. True, true,
It's a
true.
sine curve.
2
By push it up by 1, by 2.
2 sine x plus 2. Wait, the x is
Okay.
yeah,
Y equals to 2 plus 2 sine x. How about the cos graph?
cosine.
The blue graph is that 2 plus 2 cosine x. Can.
Yeah, can.
Right? That's a vertical shift by 2 unit up. Right? And there's the rest. This the previously this is the 0 line. Now it's shifted to 2. So this is the amplitude. is also the amplitude. Okay, independent variable x, just a summary. Okay, let's start our simple harmonic motion. Topic 17.1. There's a syllabus. Right? There's your data sheet. Right? 9.1. G is that. This formula is given. That one is a definition. That's the velocity. How the velocity changes with time. How the velocity changes with displacement. Right? Not to where to find your formula. Okay, let's go to introduction. Oscillation arises in many physical systems and can be observed both microscopic and macroscopic level. Study of oscillation is confined to simple harmonic motion. Equations that discuss simple harmonic motion are developed in this topic. Damping and resonance are introduced, and consideration is given to situation where this can be either advantage or disadvantage. Okay, let's go to simple harmonic motion. Any motion, what is simple harmonic motion? Any motion that repeats itself after a certain period is known as periodic. Right? Repeat itself. Any motion that repeats itself after a certain period is called periodic motion. And since such a motion can be represented in terms of sine and cosine, it's called harmonic motion. Right? Can repeat harmonic because can represent by sine and cosine curve. Simple harmonic motion, or sometimes we call it SHM for short, is the same, is the name given to a particular type of harmonic motion. The following are examples of simple harmonic motion. Right? We are looking at simple harmonic motion, perfect oscillations, where there's no resistive force, or the experiment done in vacuum. Right? So some example will be here. Right? Pendulum, just something heavy, like string, or a spring attached to a heavy object, right? Oscillating up and down. Or this one came out in 2021, May, June, paper 41. Right? For simple pendulum, the, the displacement must be less than 10 degrees. It's done in vacuum. And for a spring is vibrating, also your displacement must not exceed the elastic limit. Right? This is your trolley held between two. These are supposed to be bent, fixed between two fixed spring oscillating on a smooth surface. The surface appears to be smooth. Example from past year paper. Right? Hope you have done this experiment in your paper 3. Have you done any experiment this one?
This one, yeah, we done a lot of times already.
Good lah. This cantilever lah. Right? This one came out in 2006 June. This one came out in 2002 November. This one came out in 2019 October, November, paper 42, or 2013 June 3. This is basically the ball stimulates a positive ion, no? And there's a positive ion in the atom there, how it vibrates to and fro. Right? Vibrating atoms in the solid. Oscillations is easier to set because you can cover two topics at the same time. You can cover electromagnetic induction and oscillation at the same time. It's a it's a compulsory question, come out every year. Right? This one came out in 2011 June, paper 42, electromagnetic induction. This is an AC voltmeter. Some come out in 2008 June. Loaded test tube being displaced. Right? This is a test tube. We just push it down. It will go up and down. Okay, motion of simple harmonic, simple pendulum. Oscillation of simple pendulum in vacuum can be considered as free oscillation. Right? Free because there's no resistive force. In free oscillation, no loss of energy, no resistive force, no gain or loss of energy. Thus, oscillation is of constant amplitude. Right? We recognize the amplitude is constant, no resistive force, no external force applied to the oscillating body. Right? We didn't push it, we only displace it initially. After that, we let it go. We don't push it continuously. That's called force oscillation or external forces. There's no air resistance in the vacuum. In this case, the kinetic energy transforms to potential energy and vice versa. Total energy is constant. Right? When we say total energy, in this case, we mean kinetic plus potential energy. Okay. Usually we want to start, we have to, this is called the rest position. Because this is where, this is also the equilibrium position where it's not oscillating. So you want it to swing, you lift it up, then it will swing to and fro. Right? The reason why it's less than 10 degrees, so that the arc there is very close to a straight line. Right? So we can consider example of your oscillation, simple harmonic motion in vacuum. Angle is less than 10 degrees. Right? You start on here, or position 2, and then you move into the right. Right? Oscillating simple pendulum in a free oscillation. When the bob is displaced, it oscillates. The bob swings between two limits. Right? There's a two limit, 1 and 3, or A and C. Right? It swings to and fro continuously, to and fro. Maximum and minimum displacement. Actually, minimum displacement is just this part is positive, this part is negative, that's all. Okay, so this one magnified to be a curve, but when it's 10 degrees or less than 10 degrees, it's more like a straight line rather than a curve. Right? So that's the rest position B, or we call it equilibrium position. Rest position is where the pendulum is at rest. When it's not swinging, it's at rest. That's the rest position or equilibrium position. Okay, we started at B, or sitting to the right, moving to the right. Okay, this one from B to C is a quarter of a period. Right? The whole oscillation is one period lah. So it takes from B to C is a quarter of period. From C to B is a quarter of period. That's half a period. Then from B to A is another quarter of a period. So it's 3/4. From A to B is another quarter. So it's a period. So if we think in terms of displacement, right, it will be 0. Then a quarter of period later will be x naught positive, and another quarter period will be b 0, and another quarter period will be minus x naught, and then 0. Right? To fill out all these kinetic energy, right? Remember This is ground level. Right? This is ground level. So this one will have maximum kinetic energy or maximum velocity. Right? This one will be maximum potential energy, zero kinetic energy. Then its potential changes to kinetic completely, maximum kinetic here. So it can move either to the right or to the left, depending on where it's moving. Right? That's how you fill up maximum kinetic energy here. Zero here. Right? Then it comes down again to be maximum, zero, and maximum again at A. Come back to B. At A is zero, sorry. At B is maximum again. Right? Kinetic energy doesn't have a positive or negative value. It's always maximum. And from there, we can, right? If we start from moving to the right, then this is your velocity, V naught maximum velocity. And at C, velocity must be zero. Zero, zero kinetic energy. You can fill up potential energy first. Where kinetic energy is maximum, potential is zero. Zero kinetic, maximum potential. Okay, kinetic energy is zero. Zero there. This one is moving to the left. Let's move to the left. That's why I put a negative sign there. Right? It's a vector. At A is zero kinetic energy. B is B naught. Right? Acceleration must be zero at B because it is maximum kinetic energy, maximum velocity. If not, it cannot consider as maximum velocity. So acceleration must be zero. Right? Where the velocity is zero here, acceleration must be maximum, but in different direction. Right? Opposite to negative shows is opposite to the displacement direction. That B again is zero. And then at A is A naught. Okay. Any comment?
No.
Okay. Okay. Looks like we have to stop in 10 minutes time. Oscillator is an oscillating particle. We are looking at an oscillating particle or oscillating point source. Right? Whereas compound pendulum, we are looking at an oscillating body. So we are not interested in oscillating body. We think of the bob as a point mass or particle. That bob there, right? Usually we think of it as circle, but you can have a heavy object there, heavy mass there. So symbol V naught is maximum velocity, A naught is maximum acceleration, EK naught is maximum kinetic energy, EP naught is maximum potential energy, T is a period. Right? Time for one oscillation is T. Time to move from A to B equals to time to move from B to C, and from C to B, and from B to A. Right? Each of them is a quarter of a period. Velocity, right? We can summarize it in terms of diagram. Maximum velocity here as it starts, so it must decrease. Moving to the right, where you start there, velocity, it decrease, and then it is zero here. Then after that, it reverse direction. Right? Remember now the acceleration is to the left. Right? Acceleration is always opposing displacement. This positive direction, So acceleration is moving, it's always left hand side, maximum here. That's why it's zero velocity. Look, undergo deceleration. So in this case, if you are looking at this case, it is increasing velocity. Okay, in this case, it's decelerating. Right? Velocity is decreasing. So maximum velocity is at right, is maximum acceleration at this part. Right? So it basically in a fixed position, the velocity is the same. Sorry, the speed is the same, but velocity has different direction. One is moving to the right, one is moving to the left. Same here, right? At this position, one is moving to the right, one is moving to the left. Same here at B, right? When it's moving to the right at the start, and when it return, it's moving to the left. Right? Because it has inertia at this time, it will move to the left, right? And then velocity is zero at this point. Then we move backwards again, right? So two times, so the speed is the same here, right? Particle position, but their velocity is in different direction, right? One is moving to the right, one is moving to the left. Right? At zero displacement, position B, x equals zero, the acceleration is zero, and at maximum displacement C, the acceleration is maximum, but it's opposite to the displacement. Right? There's a positive x displacement, that's a negative acceleration, so acceleration decreases to zero. Okay, in this
Yeah.
part is negative displacement, so acceleration is positive. An oscillation is a to and fro motion between two limits. These are the limit A and C. Right? We move from B to C, back to B, back to A, back to B. One oscillation or one cycle is one complete to and fro motion about the center or between two limits. Right? So you start from A, you go to B, you go to C, comes back to B, goes back to A. That's one oscillation. Or if you start from B, it goes to C, goes to B, goes to A, and comes back to B. That's one oscillation. Period of an oscillation is the time to complete one oscillation. Right? Same as wave lah. Period. Frequency. Right? Either we use a Greek alphabet nu of f. Oscillation is the number of complete oscillations per unit time. Unit is hertz or cycle per second or just per second. Right? Frequency is 1 over t, same as waves. Amplitude, sometimes we use x naught, some people will use a or r because it's related to circular motion. It's the maximum displacement of the oscillator from the rest position. So that's the amplitude. Rest position or equilibrium position is a position where the object is not oscillating. When it's not oscillating, it will stay at B. Right? In circular motion, we call it angular velocity, but in simple harmonic motion, we call it angular frequency. It's the same now, except it's oscillating horizontally or vertically, that's all. Right? We represent Greek alphabet omega. of an oscillating motion is the frequency expressed in radian per second. Right? All these you need to memorize. Omega is 2 pi f. Same as circular motion, where f is the frequency of oscillation. Okay, we define simple harmonic motion as a motion in which the acceleration of a body is proportional to displacement from the fixed point, always directed towards the point. Right? Or we summarize with A equals to minus omega square x. This memory word, acceleration and displacement are always in opposite direction or always directed towards the point. Either way. Right? This is the differential equation. We don't need to, so the solution to the differential equation is this one or that one there. Right? For your syllabus, just use this one. You can do that. I think you will study that in your further maths. X naught is the amplitude of maximum displacement. Omega is the angular frequency in radian per second. So we will use equation x equals x naught sine omega t. This is where the oscillation, the particle there or oscillator there move to the right in the positive x direction. Right? Or we can represent it with a sinusoidal sine curve. Where B is the 0 point. Right? B is where it comes here. C is where it goes to the maximum. Right? If we start from oscillating from C, this is a cos graph. Right? It may cut off soon. So if you have spend your time trying some of the question, if you can, I can go faster.
Okay.
Same. Okay with that?
Yeah.
Show that for small angular displacement less than 10 degrees of the bulk of simple pendulum, show that the motion is simple harmonic. The period is given by